Hi everyone, thanks for being here. My name is Zhang. I am a third-year PhD student at WashU, and today I'm super excited to share with you our recent work, deep learning-based causal inference for large-scale combinatorial experiments, theory, and empirical evidence. This is a joint work with Zikun, Dennis Zhang, Heng Zhang, and Renyu Zhang. To begin with, the motivation behind this project comes from A/B tests, which are common practice for online platforms such as TikTok, Google, Meta, and Amazon, and so on. Normally, those kind of large-scale platforms will run over 10,000 A/B tests annually, and hundreds of A/B tests will be running simultaneously. Therefore, with that large amount of A/B tests, one thing is really interesting is about the treatment effect of multiple A/B tests. To illustrate this idea, I would like to use this concrete TikTok example. So here is the TikTok app interface. And now let us assume that TikTok is launching 2 experiments to increase the user's video watching time. What are those 2? In experiment 1, there will be a get reward sticker, meaning that the randomly selected treated user will be given this get reward sticker on their TikTok app interface on the top left of their interface. And in experiment 2, the randomly selected treated user will be given this send gift sticker on their comment area. The control users in those tests will have nothing on their interface. Now, the major question here will be how to estimate and infer the combined treatment effect of multiple A/B tests. In this specific example, it will be how to estimate and infer the ATE of having both stickers. Apparently, there were some naive and simple solutions, and solution 1 will be a linear addition, meaning that we simply adding the effect of a reward sticker and the effect of a gift sticker as the effect of having both stickers. The limitation of this simple method is that it ignores the nonlinearity of treatment effect. What does this mean? Well, some users may have marginal decreasing, meaning that those experiments have negative interaction within each other. The users might get really tired of seeing so many stickers and he doesn't want to use this app anymore. Or on the other hand, there will be some users who have marginal increasing. They are super excited about seeing all those stickers flying all over their interface, and they may want to explore more and spend more time on this video and watching behavior on these platforms. Apparently, this linear addition failed to capture neither of those marginal decreasing or increasing patterns. Well then, how about we just run a full factorial design? Here we can run all treatment combinations of these 2 treats, where we will have a no sticker and having separate sticker settings and having both sticker settings. The limitation of this method is that exponentially large treatment combinations. Suppose that we have m binary level tests, which will generate 2 to the power of m combinations. It is now impossible for us to assign even 1 user to each combination if m is larger than 13. Therefore, to restate our research questions, what we want to solve in this project is without observing outcomes of all treatment combinations. First, how to estimate and infer the average treatment effect of any treatment combinations. And second, how to identify the optimal treatment combination with the highest effect. What I want to point out here is that our research is more focusing on a post-experiment analysis with the minimum interference of the current experimentation platforms. And because of time limit, our main focus on solving the first problem is that how to estimate and infer the ATE of any treatment combination. To give you a preview, in this research, our solution and contribution can be listed as follows. First, we provide this framework to solve the important problem with valid inference by combining both deep learning neural network to capture experimental interactions and heterogeneity with double machine learning to ensure a valid causal inference. And what we want to emphasize here is that we believe we're the first to validate the double machine learning type of estimator using large-scale experimental data in our empirical evaluations. And this research speaks to the literature in double machine learning in valid estimation and inference with multiple experiments. And last but not least, the experiments on online platforms. Now it's time to dive into our deep learning framework, our theory part. The setup is as follows. The platform runs n A/B tests, each with a binary treatment, and we will use this T vector to denote a treatment combinations. For example, if we have 4 experiments and T equals to 0010, it represents that the user is in the control condition of experiment 1, 2, and 4, and in the treatment condition of experiment 3. We have outcome Y and covariance X with n observations. The important assumption here is that the observed data is generated by a semi-parametric form, expectation Y, outcome Y, given covariance X and treatment combination T equals to this G theta star X T. Here, the theta star X summarize uses covariance, and G theta X T is the link function to link theta star X and treatment combination T together for predicting outcomes. Here, this is the key to capture the interaction between experiments. And theta star X here is unknown and high dimensional. Therefore, it will be learned by machine learning models. Before we go to the next step, I would like to elaborate more on our choice of link function. Here in this multiple experiment setting, we're using this generalized logistic link function, since we believe this link function is suitable to capture any marginal decreasing or increasing pattern that we mentioned previously. Here is a simple example of how it captured the marginal decreasing with 2 experiments, T1 and T2. Suppose this is the response of Y in this link function, and under the both control conditions, the outcome Y will landed on this red point. While adding 1 experiment T1, the outcome Y moved from the red point to this blue point. Adding 1 more T2, the outcome moving from blue point to the green point. And this just illustrates the marginal decreasing with 2 experiments for this user. By changing X, we may change the theta 0, theta 1, and theta 2, and we may be able to move the 3 points to the left of this figure. Therefore, it then captures the marginal increasing with 2 experiments. And now let's go to the next step. Within this framework, what we want to achieve is the goal that given the data generated by this link function, and this with only partially observed treatment combination T out of 2 to the n power of n possible combinations, we want to estimating and inferring the average treatment effect ATE for any combination T. And it is defined as this mu T as the expectation of outcome given T minus the outcome given the control conditions. So T0 here just representing during the control conditions for all treatment. Also, we define this best treatment identification T star, which maximizes the mu T. Here, to achieve this goal, we're employing a 2-stage method. On the first stage, we want to use the deep learning neural network from observed data to get this estimator theta hat. And on the second stage, we will construct the ATE estimator using first stage results. That is asymptotic and normal, so that we can perform causal inference using this ATE estimator. Now let's see how it works. So the first stage will be a deep learning, and we employ this structural DNN. By structured, it means that only feature X will go through all those hidden layers and then get theta X. Treatment combination T will at last concatenate with theta X, and they will go through this link function G together. By solving the empirical loss minimization problem, it will give us the empirical estimator of theta star, which is this theta hat. After this first training stage, we came to the second stage of construct an estimator. The naive approach of constructing this estimator will be a plugin estimator, meaning that after getting an estimator of theta hat, one can immediately construct this plugin estimator by replace the theta star X with theta hat. So here we construct this naive estimator of ATE mu PIT and the best treatment identification estimator, this T hat star. Here, unfortunately, I want to say that those two estimators are invalid for causal inference, since theta hat has not fast enough convergence rate. So to solve these problems, we turn to a Niemann orthogonal score function. What does this mean? It means that we need to find a score function psi that satisfies the following conditions. The first is this zero order conditions, meaning and which is the common conditions for most score functions. And the second one is the Niemann orthogonality, meaning that the derivative of this expectation of this score function with respect to theta, when theta is around its true value, will be zero, which implies that the estimator is actually robust to first order errors in theta. And we're able to show that under mild regularity assumptions for any treatment combination T, this Niemann orthogonal score function looks like this, and it's just a plug-in term with a de-biased term. And what's more, we can show that under non-restrictive regularity assumptions and cross-fitting, employing this Niemann orthogonal score function will give us a valid estimator to perform causal inference. And we can actually construct the confidence interval using the equation here. So here is basically our theory framework. And now I would like to show you how this framework can be applied to a real-world field experiment setting. Here, we collaborate with one of the top 3 short video sharing platforms in the world, who enjoys over 300 million daily active users, over 500 million monthly active users, and can generate over $20 million as revenue per day. And we consider the 3 concurrent A/B tests on the recommendation system upgrades of 3 pages respectively, their discover page, live page, and for you page. So during January 10th to February 1st, 2021, over 200 million users were targeted in this field experiment setting. The outcome why we're interested in is the video watching time of users, and we can obtain the demographic features and their users' past behaviors as the user feature X. The treatment combination vector T is a 3-dimensional combination vector. So in practice, normally we will partially observe 5 of 8 treatment combinations. Those are the absolute control condition 000, the absolute treated condition 111, and the single experiment in between those 5 combinations. However, luckily, in this field experiments, we're able to get the ground truth ATEs of 8 treatment combinations, which then enable us to actually validate how this framework will work in predicting those unobservable treatment combinations. And before we actually show our results, I would like to introduce some benchmark estimator that we're comparing with. The first one will be this linear radiation. As we just mentioned previously in the motivation solution part, we're assuming that the ATEs of different individual treatments are linearly and independently additive. This is really naive, but it's simple and it's actually being used in industry. The second one will be a linear regression. It regresses Y on X and T and then predict the outcomes of unobservable treatment combinations by linear extrapolation. Still a linear approach, but it better leverages the user features. The third one is a pure deep learning one. Here we regress Y on X and T, use a deep neural network. And the fourth one is a structured deep learning, meaning that here we apply the same structured DN as our d-biased deep learning estimator without d-bias. So it's just a plugin estimator at the second stage. The last one is the framework we proposed, this d-biased deep learning estimator. It's just a structured deep learning estimator with an Niemann orthogonal score function. So by comparing this DEDL with SDL, we highlight the value of bias correction through orthogonality. And here are our main results. First, our DEDL estimator outperforms all benchmarks. Again, we want to emphasize that we believe we are the first empirical validation of double machine learning type estimator in practice. And to show the performance, we provide this mean absolute percentage error of 5 benchmarks. As we can see, the y-axis is the MAPE over unobserved treatment combinations, and DEDL actually outperforms all other benchmarks by having the lowest MAPE. It only has 1.75% of MAPE. And we want to show that the result is actually robust to MAE, MSE significant level, and all other treatment combinations as well. The second result here is that actually parametric link function reduces prediction accuracy. However, d-bias through Niemann orthogonality increases AT estimation accuracy, and the benefits of B outweighs the cost of A. How is that? Here, the same MAPE error here is that we can see that by comparing PDL and SDL estimator, the parametric link function employed by this structured deep learning actually reduces the prediction accuracy by increasing the MAPE of SDL. However, by d-bias through Niemann orthogonal score function, it increases AT estimation accuracy by reducing this MAPE from 30% to 1%. So the benefit of B actually outweighs the cost of A. The third main result is for practitioners is that when does the DEDL actually work? So the DEDL works as first stage DNN converges. To illustrate, here is the figure of this DNN validation loss at the first stage within the increasing of training apple. As we can see, and here the green line and the blue line are the MAPE of SDL and MAPE of DEDL estimator respectively. As we can see here, both DEDL and SDL estimator yield smaller MAPE as DNN training loss is getting smaller. However, the SDL estimator, meaning the structural deep learning estimator without d-bias, has bad performance, even with well-trained DNN. And one important implication here is that this kind of double or d-bias in double machine learning is not for free. One should train machine learning well at the first stage. Otherwise, the d-bias cannot save your estimator anyway. So for takeaway, we provide this DEDL framework, which can provide an estimator with probable theoretical guarantees and good empirical performance for analyzing multiple experiments. And this double machine learning type estimator works very well in practice with real experiment data. The framework actually is currently utilized by the platform. And here comes to the end. Thank you. And feel free to contact me if you have any questions.